So we're looking at related rates of change. So what we've talked about already is that when we differentiate a function, we get the rate of change. The problem is that sometimes there are other things that are in the relationship that have to be a part of what we are doing. So a related rate of change means that we are probably doing more than one derivative to find the rate that something's changing. It may be that we have to differentiate it in terms of one thing and then that in terms of another. So the rate of change is the rate So we've been writing this as dy by dx, the rate y changes with respect to x, all right? So it doesn't always have to be a y and an x. Now we're into actually applying it to things. We will get things like dA by dr, the rate at which area changes with respect to radius in this particular case. All right, or we may get something like dr by dt. The rate the radius changes over time. So you can see that these two things actually could be related. So we could be changing the radius of something, because obviously we're not talking about something that is not changing. So we're not talking about a fixed circle area. We're talking about a circle that is growing or shrinking. So therefore there is a time element to the area. We need to know what the area is at a specific time. But to know that, we need to know how much the radius is changing at that time, and therefore how much the area is going to change by the radius. And that's that relationship, that relative rate of change that we're trying to get to. So let's have a look at an example, because that will develop the skills. E.g. I love this purple pen. Need another one. The volume of a cube with side x is changing at a rate of 6 meters per second, meters squared per second, meters cubed, because it's our volume. Find the rate at which getting to surface area. Right, not even in the question surface area, but we're still going to look at that. So we're going to say length and SA is increasing over time. So one of the biggest hints you can have is the measurement unit. That gives you an awful lot of secrets. So the measurement unit here is this, all right, meters cubed per second. That tells you that you are probably going to be looking at volume over time. It gives you one of the things you need to know. So you've been given volume. The volume is changing over time by 6 meters cubed per second. All right, so the link here is that this is time, seconds, and this is volume, meters cubed. So you can figure out what you're writing at the front based on what you're writing at the end. All right? So you look really carefully for those sort of things. So the first question is find the rate at which the edge length is increasing over time. So what we know about a cube is, and we have to know some things, and you'll find on your formula sheet you do have quite a lot of formulas that you can use to do these particular problems. But what we know is that the volume of a cube equals length cubed. Right, we've decided it's length. All right, so length cubed. So if we know that already, we can find what? If that's a formula that we've written down, what in this paper would we be expected to do next? Yes, differentiate, obviously in the differentiation paper. Okay, so dV by what do you think? Only L there, so let's DL it. Equals 3L squared. All right? So far, we haven't gone anywhere though, because we want to know the rate at which the length is changing over time. So we're looking for the rate of change of length over time. All right? So have we got enough things now that we can manipulate to find this out? We need an L, we've got an L. We need a T, we've got a T. And luckily enough, we've got two dVs, which will cancel out if it's written properly. So this particular sentence here, dL is really important. That's our related rate of change. So we've got two rates of change that are related to give us the answer. And we are going to cancel those out to give us what we want. All right? So dL by dV we don't have, but we do have dV by dt. It's 6. But we do have dV by dL. So flip it. 1 over 3L squared. So 6 over 3L squared or 2 over L squared is the rate at which length is changing over time. So if we were asked for when time equals 4, how would we find out this answer? Sorry, when length equals 4. So when the length equals 4, trying to find out the rate at which length is changing when it is 4. We'd go back to here, we'd substitute in our 4 here. So at L equals 4, we're going to get dL by dt equals 2 over 16 or 1 over 8. What's the units here, guys? Right, so look at the front. It will tell you the units. So meters, seconds, meters, and I know in physics and science you run it like that, but you can't just write it over the top. It's the same thing, right? ms negative 1 is the same as m over s, right? That's the mathematics behind it. So in science they teach you to write with negatives. In maths we're happy with either. We do tend to try and follow the science so it doesn't get too confusing though. So the second question is about surface area. So we know the formula for surface area. Surface area equals, right, Q, boom, 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 boom. Three-dimensional figure, surface area, 6 sides by L squared. 6 sides, each one L squared. All right? Happy with that? So what could we do next? Differentiate. So what are we going to differentiate it by? L, because that's all we've got. 12L. All right? So if we've got 12L, then we again are trying to look at that related rate of change. We're looking for the rate at which surface area is changing over time, or when L equals 4 we've gone for. So surface area, how is it changing when L equals 4? We still need it to be changing over time, all right? So we're still looking for dSA over dt when L equals 4, all right? So it's changing over time, so our formula is going to be dSA over dL times dL over dt, all right? So this one, we've got 12L. This one, we've already found. Here it is, dL by dt. It's 2 over L squared. So we may have to use something we've found before. Times 2 over L squared. Put them together, and we've got 24 over L. So again, when L equals 4, dSA over dt equals 6. What's the units? Meter squared for area over time. So what is this actually telling us? All right, we are trying to find out how much something is changing at a relative spot in time. Okay, we could have also been asked here to find the surface area when L is something. That would have been easier. We would have just gone into here. So that's the sort of questions we were doing yesterday. Just differentiate once and stick something in. We've now been asked to find it when L is 4, okay, and therefore what that at that time. So the time is still moving, all right? But when the surface area has a length of 4, so 4 times 4 is 16 times 6 is whatever, we are trying, that happened here. So you've got a cube, right? Has a side of 6 centimeters on each side, 6 meters. So the cube is 6 meters cubed volume, right? And its surface area is 6 squared times 6, which is 6 cubed. So it just happens to have the same volume as surface area, but that's okay. And we're not asking what the surface area is. We're asking how fast is it changing at that precise time? How big is it growing by? This is a cube that is growing by changing the length of the side. So when the length equals 4, it's changing by 6 meters squared instantaneously per second. Now you've got no way of knowing that without calculus. All right, it is a split second in time. Okay, so that is where relative rates of change are different from physics. Okay. So that's it. We're going to do some practice now.